Okay, so this is, what chapter is this? This is chapter 31? And we're going to do number 11. So number 11 asks you, what is the ratio of the velocity of a beta particle to that of an alpha particle if they have the same non-relativistic kinetic energy? Okay, so we have to figure out the ratios of their velocities. We know what alpha particles and beta particles are, whether we realize it or not. Do we know what is a beta particle? Another name for a beta particle. Maybe we don't know what it is. What's a beta particle? We got beta particles and beta decay. I should write the authors of the book, because clearly this is not clear. Beta particle? It's just an electron. Typical beta negative particle. So what's a beta positive particle? Nope. Beta positive particle is a positive electron, something we call a positron. So it looks just like an electron, except it has a positive charge. Yep. So that's what a beta particle is. That's what a beta plus particle is. That might make life a little easier. Now that we know that. And then we also have alpha particles. We should actually know what that is from a previous chapter. What's an alpha particle? It was used in a famous experiment in the gold foil experiment. They shot alpha particles, which are also... Charlotte, what did you say? Yeah, it's a helium nucleus. So I'm going to write with this HE with the little 4 up top and a 2 down bottom. What does the 4 mean? You can also write it in the general format. A, Z, N. What is A? Mass number. And what is the mass number? How do we get to it? Number of protons plus the number of neutrons. What's Z? Number of protons. It's also the atomic number. It's also the number that you use to find the element in the periodic table. So if I go look up helium in the periodic table, what's the number that it goes along with it? 2, because there's 2 protons. And then what's N? Number of neutrons. So here with helium, I've got a mass number of 4. That means I have 4 protons plus neutrons. If I have 2 protons, how many neutrons do I have over here? You take this number plus this number to get 4. So how many go here? 2. Okay. I'm curious, how many of you did this in chemistry? You should have done this stuff in chemistry. How many have not done this in chemistry before? Raise your hand. Haven't taken chemistry. Okay, you're gonna know more about chemistry than anybody else in that class then. Yeah, just a disadvantage in here. So what we have to do is we find the ratio of the velocity of a beta particle to that of an alpha particle if they have the same energy. So we have an equation for energy of these things that are moving. What's the energy of something that's moving? It's called kinetic energy. And what's the equation for that? 1/2 mass times velocity squared. So the kinetic energy of a beta particle is 1/2 times the mass of whatever the particle is. What is the beta particle again? An electron. So this is the mass of an electron times the velocity of an electron squared. And then the kinetic energy of an alpha particle is 1/2 mass of an alpha particle times velocity of that alpha particle squared. So this isn't any kind of general equation you can memorize. It's a process that you're following based on what they ask you to find. They asked us to find the ratio of the velocity of a beta particle to that of an alpha particle. So I basically, that ratio, I need to find V beta over V alpha. I need to find what that is. So this is what I'm looking for. We know that because of the wording of the problem itself. But it's in a very specific situation if they have the same non-relativistic kinetic energy. So that means that I can set these two kinetic energies equal to each other. I can say that kinetic energy of beta is equal to kinetic energy of alpha. So I can take 1/2 mass of the electron, which is the beta particle, times velocity of the electron squared, equals 1/2 mass of the alpha particle times velocity of the alpha particle squared. I'm looking for V beta over V alpha, which is V electron over V alpha. So I want to get that on the left side and get everything else over onto the right-hand side. So I can do some algebra. Is there anything that I can cancel out of this to make my life easier? I have a 1/2 on both sides, so I can divide both sides by 1/2. 1/2 goes away. Trying to get V beta or V electron over V alpha, so I divide both sides by V alpha squared. If I do that, I get mass of electron, V electron squared over V alpha squared equals mass of the alpha particle. That's all we have left over on the right-hand side. Again, is this what I want to solve for? I want V electron over V alpha. I want that all alone. So now I divide both sides by mass of the electron to move the mass of the electron. I'm trying to isolate V electron over M alpha. So divide by mass of the electron on both sides. Mass of the electron will cancel out. And end up with V electron squared over V alpha particle squared equals mass of the alpha over mass of the electron. Now how do I get this to just V electron over V alpha? Take the square root of both sides. Take the square root of the left, square root of the right. V electron over V alpha particle equals the square root of the mass of the alpha particle over the mass of the electron. Now we do the masses, plug in our masses. Velocity of the electron over the velocity of the alpha particle is equal to the square root of the mass of the alpha particle over the mass of the electron. So what are those two things? What are those two values? So what is the mass of the alpha particle? We need to get that in kilograms. So usually when they get masses of particles, the mass of helium we can get from the periodic table. If we go to the periodic table, we get a mass that looks like this, 4.002. And that has specific units. That has units of U. AMU's atomic mass units. Is that a mass that I really want? What mass do I probably want? What do I want to get the mass in? What unit? Grams, or what's the SI unit is kilograms. So there's a conversion factor between U and AMUs in kilograms. And this is given in the lecture. I talk about it in the lecture. 1.6605 times 10 to the negative 27 kilograms in 1 AMU, 1 atomic mass unit. So I go there, and that gives me my mass of my helium. I actually didn't calculate it. So take out your calculators, and let's calculate what that massive alpha particle is. Type that in. The mass of helium is 4.002 U's, 4.002 AMUs. This is in the periodic table, times 1.6605 times 10 to the negative 27 kilograms per AMU. Multiply that number out, let's see what we get. Get your answer and then whisper to the person next to you, see if you get the same thing. And whisper to everybody else at the table, see if you all get the same thing. As soon as everybody at the table gets the same thing, one of you at the table raise your hand. What'd you get? Times 10 to the negative 27 kilograms. Is that what we got? Yeah? 2 tables got it, must be right. The other 2 tables are just silent. So that's the mass of our helium. We plug that right in. 6.64 times 10 to the negative 27 kilograms. And then we divide by the mass of an electron. What's the mass of an electron?
So you could just do
9.11 times 10 to the negative 31 kilograms. Plug those numbers in. You should get that the velocity ratio is about 85.4 to 1. Are there questions on this? Any questions? I have one. So it's the first time I've taught this class, so every time I teach a new class, I learn a lot the very first time I teach it. That's why all your grades end up keep getting curved up, because I'm giving you extra points and extra grades to help your grades out, because it's the first time I'm teaching it. So I'm learning what I probably need to talk about better when I teach it next time. I'm curious, how many of you know where that came from? I told you where it came from. Where does it come from? What about where in the periodic table?
It's under the
Under the symbol? Yeah. How many of you have computers? Bust out your computers. I want you to tell me, if I wasn't doing an alpha particle, if I was doing, let's say, beryllium, what would I use for that atomic mass number, AMUs for beryllium? What is the atomic mass of beryllium in AMUs? So find a periodic table, you find the symbol, and find a number that's kind of written underneath that. What do you get for beryllium?
9.0122.
Okay, 9.0122. Everybody find 9.0122?
Periodic table for kids.
Yeah.
Oh, that's what I know. Isn't that like grams? Is that not grams? I always, it's a.
That's the mass number in AMUs, in atomic mass units. So you have to convert that number to get it into the SI units, to get it into kilograms.
Because like when you do conversion in chemistry, I always put it in grams per mole. I guess is that the same thing? I don't know.
Grams per mole.
And that's
So there's a conversion, grams per mole, to get it into just plain kilograms. Yeah. We don't bother with grams per mole. We don't like moles because we don't like cancer in physics. Chemists like cancer. We're getting this on video, so it's well recorded for the 3 people that actually watch these. Okay, so the other questions I was asked were largely about the doing the radioactive decay questions, basically 17 through 20 something. The decays are actually pretty straightforward once you know what you're doing. They're basically just little puzzles, and the key to the puzzles is knowing 3 equations and knowing what these various quantities represent in these equations. So Z tells you the number of protons inside of something. X is going to be a symbol for an element. You can go back later and rewatch the lecture. That might help, or you can just rewatch this because we're going to go over how all these things work. N is the number of neutrons. And A, as we said, is the mass number. And what did the mass number tell you? Number of protons plus neutrons. And when you're doing radioactive decays, they give you a kind of a key to follow for each different type of decay. For alpha decay, you have whatever your element is, X. That could be anything. It has N neutrons, Z protons, and A is its mass number. And in alpha decay, you're going to end up with some other element, some other symbol. We'll figure out what this is. You're gonna end up with an alpha particle in there, a helium nucleus. Helium. What was the mass number of helium? 4. How many protons for helium? 2. So how many neutrons for helium? 2. And anytime you're doing a decay, you have to conserve charge. So I need the same number of charge on the left-hand side as I have on the right-hand side. So I can use this general format to figure out all the numbers that I'm going to have. So my A, I can't have A as my mass number anymore. That would change my charge. I need to subtract off the nucleons that I have in whatever my other piece is. And I have 4 nucleons in there. So I lose 4 nucleons. A minus 4. How many protons does helium have in it? How many? 2? How'd you get that? 2 plus 2. This number right here, the number on the bottom left, that's the number of protons inside of your atom. So I can't have the same number of protons. I can't have Z, because 2 of the protons go into this helium. So I have to subtract off those 2 protons from the Z that I would have for this new element. So that's got to be Z minus 2. And what happens to happen to the number of neutrons? Can I have the same number of neutrons? Nope, I need to lose a couple neutrons too. N minus 2. Because those 2 neutrons go into the helium. Okay, so there's an alpha decay. Alpha decay. Pretty straightforward. General equation for, do you want to do an example of an alpha decay? Let's do an example. Pick an element. Any element in the periodic table. Cobalt. Okay, so instead of using X, which is just a general symbol, we're going to use the symbol for cobalt. What's the symbol for cobalt? CO. So we've got a nice little CO here. What is the number of protons in cobalt? So we need to find its atomic number. Let me see. Cobalt should be that number that's just in the very, very top of the periodic table. So what is it? 27. So we got 27 right here. Okay. If I look at the periodic table, I have these numbers. I have the 27 up top, I have the symbol, I have the name of it, and then I have this atomic mass number. Right? What is the atomic mass number of cobalt? It's what? 58.933. Ooh. So this is what cobalt looks like in the periodic table. You've got the 27 up top, then you've got the CO, and then it might say cobalt if you're lucky, and then it has this number down at the bottom. What is it? 58.933. This number, the atomic mass number, that tells you the number of protons and neutrons you have. But can you have a fraction of a neutron? That's a fraction, right? So what you have to do with the atomic mass number, you basically have to round it. So what would that round to figure out what the A is? That would round up. That would round up to 59. So my A, my mass number, is going to be 59. If that's my mass number, how many neutrons do I have? How can I figure that out? I know that this number is the number of protons plus the number of neutrons. So if I take that number of protons, I do 59 minus 27. What's 59 minus 27? 32. So I got a 32 right there. So what tool, if I give you a decay thing on a exam, figure out these decays, what do I need to also give you? Periodic table. You need a periodic table to do these. So now we can figure out what this is. We can figure out what happens. So I take my A, whatever it is, and I subtract 4 from it. This is the general equation. Put this on your cheat sheets. Take my A, subtract 4, what do I get? What's 59 minus 4? 55. What's 27 minus 2, right? I take my Z, which is 27, minus 2, what do I get? 25. I take my N, my number of neutrons. Subtract 2. What's 32 minus 2? 30. I make sure I did my math right. The number of neutrons plus the number of protons should equal the mass number. 25 plus 30 equals 55. I need to know what symbol to put in here. Which one of these three numbers do I look at to find the symbol? I look at the 25. The number of protons is always the number in the periodic table. That determines your element. So what is 25? Manganese. What's the symbol for that? Mn. So now I've ended up with manganese. What's the atomic mass of manganese, according to the periodic table? 54.9, so we have to round that up to 55. Yeah. Okay. And then what else do I need? Right, this isn't balanced yet. I'm doing an alpha decay here, so what am I missing? General format's up here. I have this X, there's my X. I have this Y, there's my Y. I need to add on my alpha particle. Plus my helium. Plus 4, 2, helium, 2. Yep. General way to find any radioactive decay. If you know the general formula, you can find anything else. Something I could do on an exam, I could make up a radioactive decay type. I could say Boubard decay is special and give you the general equation for Boubard decay, and you have to figure out the Boubard decay for something. Let's do a beta decay. So what's the general form for beta decay? Basically, the beta decay general form is a cheat sheet. All these things are cheat sheets for how to do a decay. I start out with my mass number, whatever my element is. Hello? Z. My general element symbol is X, and I have N neutrons. In the beta decay, my mass number stays the same. I need to add a proton. When I add a proton, I need to subtract a neutron plus a beta particle, which is an electron, plus on something called an anti-electron neutrino. Anti-electron neutrino is completely neutral. It has no effect on the charges. Don't care about that. Electron, what's the charge for an electron? -1. So because this is -1, that's a negative charge that I'm putting in, I need to add a proton to cancel out that electron so that I keep the same Z, keep the same number of positive charges on the left and right hand side. And because I'm adding a proton, I need to subtract a neutron so that I keep my mass number the same. Mass number still has to be Z plus A, Z plus N. And this is the general form, so let's see how it works in an actual problem. Let's do, we can do one from the book, or we can do one just make it up. What do you want to do? Book example or made up example? Let's do a book example and then a made up example. Yeah? I think this is problem number 17. So they tell you there's this thing called tritium, and tritium undergoes a beta decay. What happens? So tritium is hydrogen with a mass number of 3. So they give you H with a little 3 up top. Now we have to figure out how to plug in all the other things. We have to figure out what's Z and what's N. H with a little 3 up top. What is the Z for H? Every atom is determined by its Z. Z doesn't change inside of an atom. This is hydrogen. What is the Z for hydrogen? The atomic number of hydrogen. Yeah, it's 1. Hydrogen has 1 proton. No matter what, I have 1 proton. So how many neutrons do I have inside of this tritium? I have to have 2, because I have to do 1 plus 2 equals 3. You've seen this before. You've seen tritium before. If you've ever seen Spider-Man 2, anybody seen Spider-Man 2? The one with Dr. Octopus? And he uses tritium to do nuclear fusion. This is what he's using. He's undergoing this process when he's combining things together. It's the actual nuclear reaction. So what are we going to get out of this? Well, I keep the same mass number, right? So my A just comes right over. Same mass number, A. What's going to happen to my number of protons? I get Z plus 1, so how many protons do I have here? 2. If I have 2 protons, how many neutrons do I have now? 1 neutron. What's my symbol here? Symbol is always determined by whatever this guy is. What element has the proton number, the atomic number of 2? Is what? Helium. So this is helium. So that's the first part. What else do I need to include? Plus the electron, plus the electron neutrino. As long as you know these decay general forms, these should be pretty trivial. Right? Do I want to do another one? Let's do another beta decay. Give me an element, any element. I don't care what it is. Yeah.
Question. Do you
Question,
just,
yes,
when
please.
you just write that extra part, you don't have to substitute anything in for that beta or that
This and
other
this?
symbol? Yeah.
Nope.
Okay.
Everything that this all determines what these numbers are.
Okay.
So when you do these numbers, that fixes all of that and all balances. Give me an element. I don't care. Any element. Xenon? Okay. That was a Disney Channel movie, wasn't it? They had like Xenon, and then didn't they have Xenon the sequel? That's a pity that I know that. I should have known that. What's the mass number for xenon? 131? Okay. What's the symbol for xenon? Xe. What's the atomic number for xenon? Is what, 50? 54? Okay. So how many neutrons in xenon? What'd you get, Claudia?
77.
77? Good. Okay. Now I actually do this radioactive decay. Does my mass number change? Nope, stays the same. Just move over 131. What happens to my atomic number, my 54? What does that become? Becomes 55. I add 1 to it. What about my neutron number? What happens to that? Becomes 76. What symbol is 55? Is what? And what's the symbol for that? CS? And then what else? Plus beta minus? Plus anti-electron neutrino. So that's beta decay. Let's do positive beta decay. General form for positive beta decay. I have an A, I have a Z, I have an X, I have an N. And what is that going to become? So in positive beta decay, I'm going to have this Y, whatever that is. The atomic number stays the same. Instead of adding an electron, we're going to add a positron and a positive electron neutrino. So what do I need to do to Z in this case? What's the charge of a positive electron? Positive or negative? Positive. So that means I have a positive charge here, which means I need 1 fewer positive charge here. So what number do I have to subtract from? Protons. And which number is that? Z. So I have to have Z minus 1. If I have Z minus 1 and I want the A to stay the same, what do I have to do to the N? I think I heard it, N plus 1. Okay, let's do the one in the book. So the one in the book gives you this particular element. They give you manganese, this is all they give you. Undergoes beta decay, positive beta decay. What do we get? Okay, so how do I figure out the rest of the stuff that goes along with this? I have manganese with a mass number of 50. What's the Z of manganese? How do I figure that out? Where do I go? Colorful periodic table, and what is the mass, the atomic number of manganese? 25. So I got a nice little 25 down here. If I have a 25 down here for the Z, what do I have for the N? 25. So what is it going to become? A stays the same. What does my atomic number change to? What does Z change to? 25 minus 1, I go to 24. What happens to N, number of neutrons? Goes to 26. What's my symbol that goes in there? What's the symbol for 24? Cr, which is chromium, plus a beta, positive, plus a neutrino. Can you find what's weird about this element that they gave us? They gave us manganese. Manganese does have an atomic number 25. Look at the mass number. What mass number did they give us? They give us 50. What's weird about that? In the periodic table, it's 55. So if I didn't give you that particular mass number and I just said manganese undergoes beta decay, what would you do? Would you just memorize this? Would that be right? I want to just memorize this. You go to manganese. How many protons does manganese have? 25. What's the mass number of manganese from the periodic table? I see 54.9, so we round that up to 55. So how many neutrons? 30. So if they don't specifically give you a mass number to use, you use the one in the periodic table, you might get a slightly different answer. But the only thing that changes is the number of neutrons. I still get 24. I still get 55. I still get chromium. How many neutrons do I have now? 31 plus beta plus electron neutrino. That's beta decay. Alpha and both versions of beta decay. Follow that same kind of procedure, same kind of idea for electron capture. Electron capture, you just have, you're capturing an electron, and I give you the general format for that. And gamma decay, give you general formats. Questions on that? No? Okay, the last question that came up during the quiz was radioactive decay. The half-life. What is the shape of the decay graph that you get from half-life? What was the correction? The shape of that graph for half-life? Exponential. Okay, but it's exponential decay. So there's a difference. Exponential. If I look at exponential, the exponential graph looks something like that, right? Increases super fast. If I look at the inverse square law, what does the inverse square law look like? It looks a lot like the opposite of this. Inverse square law looks a lot like that. Okay. That's a lot what exponential decay looks like. Exponential decay is just like this. So exponential decay graph looks very similar to the inverse square law, but they're not the same. When you do out the math, the half-life is exponential. I'm not too worried about that concept. The bigger concept I'm worried about in radioactive chapters is doing those radioactive decay equations. So if you practice some of those, I could see maybe giving you 5 or 10 of those on an exam for a problem for this chapter. They're pretty straightforward. Okay. Any other questions on radioactivity? Yeah. It could be alpha, anything that I gave you in the lecture. I don't remember which ones I gave. I think I gave you alpha decay, beta plus decay, and I think I gave you an electron capture formula as well. Yeah. They look very similar. Exponential decay is a little bit steeper, and that's what half-life actually does. That's how radioactive decay actually happens. Any other questions for me? Yeah, Charlotte.
I go to 37.
37? What was 37? Let's look. The beta decay equation for the neutron? Yeah. So we have a neutron, and we know that it undergoes beta decay. So neutron, what's the charge of a neutron? Zero, has no charge. So I have no charge on the left-hand side, so that means I need no charge on the right-hand side. For a beta decay, I know I have something here, don't know what it is, plus an electron, plus an electron, anti-electron neutrino. What's the charge of the anti-electron neutrino? Did it affect any of our other calculations? No, so what's its charge has to be? Has to be 0, okay? I have an electron. Electron is positive, or negative charge, right? What can cancel out a negative charge? Positive charge, and what would that be? A proton. So you have to stick a proton here. So the tricky part of that one is more, you can't use the basic guide, right? They don't have Z, you don't have a Z number, you don't have a mass number, you don't have the neutron number. You just have to know the charge. Yeah. What else could, in theory, a neutron decay into? What other kind of thing could cancel out an electron? So we could have a neutron turn into not just a proton plus an electron plus an anti-electron neutrino. Positron. Positron is a positive electron. So we got a positron, an electron plus an anti-electron neutrino. This would be another answer you could give. Still cancels out. Still conserves charge. Both sides.
You have to do the second part with
No. Any other questions? Yeah.
Question.